Chapter 10 is, I actually think there's a lot of calculating in chapter 10. It's properties of materials. So it literally goes through the different kinds of materials, the properties of materials, and it is a lot of text. It does do the stress strain curve, but we're going to do that today some more. But really, it's just a lot of reading. Good reading, if you find the time, but not a lot of calculating in chapter 10. So what I've done in the past is I've assigned you one topic out of 10 that you have to read. And then we all come in and we share. So you'll get that topic on Thursday. Today we'll finish up tensile stress, compression stress. We'll do shear stress. We will do elongation again. And then we'll do Young's modulus again, because we just did it for the first time. So some repetition. All right, homework. Or quiz. Anybody want to talk about the quiz? I think most of you did well. It was just a stress, right? It was just P over A. So the thing that maybe is confusing some is you were given an area that looked like this on the quiz, right? And it was a part of a column. So I didn't give you the column, like I didn't give you the image of a column or a post, right? But I said this is the cross section. So we have to get used to this concept of cross section because we use it all the time, right? So I might not give you the whole structure, but I give you the cross section. If it was a pipe, the cross section is, a pipe. It looks like a pipe, right? If I give you a 2x4, the cross section is a rectangle. So try to get used to that terminology, and maybe or maybe not, you'll see the actual beam or the post. But when they give you the cross section, what are they giving you? The area, right? So we know that stress, P over A, if you're given the cross section, you're given the area. And of course, if you're given the load, then you have everything you need to calculate a stress. So that's the calculated stress. It's not the limit. It's not the stress you can look up for the material. It's the calculated stress. Okay. And it's also average. So at some point, we'll not do average, but right now we're just continuing to do average. Okay on the quiz? Yeah. Homework was what numbers? 6, 10, and 11? Yeah. How'd that go? Easy peasy. Well, I like to hear. So now and then statics comes into play. This was a problem where statics comes into play in that we need to know what the load is on each section of this thing. So statics told us that everything's in equilibrium. That means every little part is in equilibrium. That means you can section something or cut it, and the left side and the right side must be in equilibrium, right? That's what statics taught us. So if I cut this thing right through here and I draw the left side, it looks like this, right? Cut it here, draw the left side, it looks like that. For me to put it in equilibrium, I got to do this. That's this piece right here. Agreed? So that piece has a 10 kip compressive load on it. Any piece of the system you can do that with. This is a pretty simple system, but it's going to get more complicated, right? I could cut it here, and I could look to the right, because either side has to be in equilibrium. So I'm going to look to the right to this little piece here, which again looks like a rectangle, but it's got 22 on it, right? And then I'm going to put it in equilibrium by going back at 22K. So this piece here feels this. That make sense? Okay, just think of like, oh, now we look at a really complicated system. Anywhere in that system, we should be able to either slice it or take it apart and understand what the inside is feeling. Because really, that's what we want to know is, hey, what are those internal fibers feeling? And how do we know what they're feeling, right? Like this one, for example, we didn't work this one, but you can do the same thing. 60K is going all the way through, and the ground must be pushing up at 60K. So if I wanted to do some kind of soil analysis, I need 60K of resistance for this thing to stay in place, right? So then I can like, oh, well, I could figure out the square footage of this down here, and that would tell me what the pounds per square foot or pounds per square inch is on the soil, right? Or I could do it right here and figure out what the stress is on this. Did they say what it is? No, some kind of footing here. No, this is the footing. Oh, this is a diameter pedestal here, right? But I think you get it. Like anywhere you can like cut it and say, oh, it's got to carry this 60K going all the way through. And if the load changes, then you can also figure out what's going on. All right. 610. Oh, 10 was a soil pressure problem. Yeah. Any questions on your homework? Anything you want to work? 11 was a hopper. So we have rods of equal loads. How many of them? Calculate tensile stress on the rod. And then hopper is supported by 3 19mm diameter. How'd you do this one? 75 kilonewtons, 19mm in diameter, 3 rods. Yeah, so it says equal loads. That one's pretty simple. So you can just calculate 1/3 the load goes to each rod. And how was it? What was the stress? Anybody got a number on 11?
88.2 MPa.
88.2?
Yeah.
Anybody else get 88.2?
Yeah. Oh, I got 88. Yeah, I got 0.008.
0.088.
I got 88 megapascals. Yeah,
88.
I think I had irregular.
Okay.
So that's like
And you got what?
88.2.
Okay.
My calculation was like
Pretty close. You
88.1.
don't round, right? We don't want to round it all until the very end, but then you can round. And then what did it say what it's made out of? Steel. What's our limit for steel?
I think 836 is 250.
250. 250 megapascals. And you're coming up with 88. So we have factor of safety of 3-ish, right? 8 times 3 is 240. Yeah, so we're about in the 3 category. Good, 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 good. All right. You don't need me to work them. I'm going to save the time. All right, turn them in. Yeah. So that was it right there, right? It was 19 millimeters in diameter.
And it's tensile stress. So
And it was a tensile stress. And it was steel. Yeah. And they did not give us the length. So I'm going to say it's 100 millimeters long. So I'm just adding on to this homework problem that you're already a little bit familiar with. And what I'd like to know is how much does it change in length? How much does it deform? We just figured out that it's safe. It's within the 250 megapascals, right? But now we want to know, like, what's the deformation? So before we do it, let's go back over that concept of how we get to deformation. Right? We first check the stresses. You did that. The stress is good. It's within the limit. If it's not within the limit, you cannot calculate a deformation. It's not predictable. If it's within the stress limit of the material, then it is predictable and we can calculate it. Okay, so that's a big concept that I'll emphasize a lot. You got to check your stresses first and then realize, oh, this is good. It's within stresses. I can calculate more things, right? If you check the stress right away and it's not good, it's outside the limit, then you're done. You don't have to check the deformation. It's like, no, this is not safe. I can't do it. Okay. So we introduced strain, and that was this epsilon. And the strain is equal to the change over L. So that's the first thing we talked about. So if we do know the change, like there's instrumentation that can give us change. Like this is a gauge that you can put on round objects. It's got little pinchers in there. So you can put it on these test specimens. Right? You can put it like they fit in there and you can clamp it down. And it's got a gauge here. And as this changes, the gauge changes. Right? So as you stretch it, it can measure deformation. So sometimes we know deformation if we have some kind of a gauge or we have a strain gauge on a bridge. These gauges here, they're measuring deformation. Okay. If we don't got it, then we can't calculate it. We can't do much, right? But sometimes we have it. So if we do have it and we have the original length, we can get strain. And that was a unit of inches per inch. It's inches per inch or millimeter per millimeter, right? If we don't have it, and we don't, we have load, we have area, but we don't have deformation. We want to know what the deformation is. If we can get these two, then we could calculate the strain, right? Or the change, because we could take the strain times L. Just massaging that formula to give me deformation. All right. So if we could get strain, well, that's when we introduced modulus elasticity is equal to stress over strain. This modulus elasticity, what is that? Is that a material property?
Yes.
Yes. It's different for all materials. It's a material property. What's this? Stress. That's P over A, right? That's something we can calculate. And then this is elongation or strain, right? So remember, if we could get this, we can get that. So now I'm going to solve for this. And it's going to be this over this. Right? Stress over the modulus. So this gives you strain. This gives you elongation. And you just calculated stress on your homework problem, right? We got stress equal to P, which was 25 kilonewtons over area, pi, 19 squared over 4. And I think you all said it was 88 megapascals. Right? So now we can do this and get that. And then we can use that times this to get that. So let's do that. Let's see how much this changed. This unit actually needed a factor of 1,000 to get it to the correct number. Because remember, a PA is a Newton per meter squared. Yeah, I think 1,000,000.
It's 836.
Huh?
Are we just doing an 836?
Yeah, we'll just do the regular A36 deal.
What is the modulus?
Good question. What is the modulus? Everybody got it?
207 e to the 2.07?
No,
207.
207.
That's 10 in the power.
Modulus of elasticity, we're in the SI unit,
Oh,
and we've got
okay.
200. Aiden,
The previous edition is 207.
seriously?
Yeah.
Wow, how could the modulus change?
Is it still e to the third?
It is e to the third.
Okay.
Weird. Well, it does change, like, depends on your steel run, right? We had that conversation, but shouldn't change in a book. That's weird. All right, I definitely need to copy these so everyone's using the same numbers. So we're getting the same numbers. Yeah, so it's 10 to the third. So it's really 200,000 megapascals. Right? 200 plus this 1,000 is 200,000 megapascals. I'll write it out too. And I'm going to take it all the way down to newtons per meter squared. Oh, wait, we have megapascals and megapascals, so we should be good. Yeah, we should be good. I won't do that. So we got 88 megapascals, and we divide by our 200,000 megapascals. And then I'm going to write it because it's really unitless, right? It is unitless. I'm going to write it millimeters per millimeter. But it's a pretty small number, I'm guessing. So that means in every millimeter, it's changing 44 ten thousandths, no, 44 hundred thousandths, geez, 4.4 ten thousandths,
For every what?
every millimeter. For every millimeter, it changes per millimeter. Yeah, that's what strain is. It's a weird unit. But we're not gonna stop at strain because really what we want is deformation, and that was this. So deformation is the strain times the original length of 100 millimeters. That's the total deformation. You take your strain and you multiply it by the original length.
We'll be left with millimeters. Wait,
Yeah, so whatever you multiply by, you're left with.
you
So-
got 24 millimeters?
Yeah, but no, more.
Is this
Yeah, I got.
1, 2, 3? Oh, 100, you're right, sorry. Yep. I was thinking 1,000. Yep,
It's like less than a hair's width.
yeah, it's super small, super small. Yep. And that's because we were like factor of safety 3, right? Yeah. Numbers get really small in the metric system. I mean, they get pretty small in the US system too, because we don't like a lot of deformation. But they get really small in the metric system. All right. This is big, like this is a really big concept. And it, not unfortunately, but maybe fortunately, it expands. And I'm gonna expand it the way the book does to give you some more kind of useful formulas. This is stress, right? And what's it equal to? Formula wise? Yep, P over A. Okay. This is strain. And it's equal to,
That's epsilon, right?
that's epsilon, yep. This is my epsilon. I don't know how to make it any better.
Deformation.
Deformation over original length. So it's both in tensile and compressive and in shear. We have shear strain. So we're going to talk about shear in a little bit. But we have compressive strain because that means it's compressing. That's a different strain than tensile strain, which just means it's stretching, right? Kind of the same dynamic, but in opposite directions. And then we have this thing called Young's modulus. And Young's modulus talked about the graph a little bit. And that there's a straight line region to the graph where we have load over area or stress going up one side of the graph and strain going up or across the other axis of the graph. So really, this is deformation because the original length doesn't change, right? It's delta over L, but L doesn't change. And this is really P over A. So you'll find the graph also shown as load and deformation. It's the same graph. But we do call it the stress strain graph. Chapter 10 will call it the stress strain graph. And it just means when we load something, it stretches. You load it some more, it stretches a little more. You load it some more, it stretches a little more. You load it too much, now it's not predictable. Right? So during that region of loading and unloading where it is predictable and elastic, comes back to its shape. That is called the elastic region. And this is where E lives. Modulus elasticity. It lives where the stress and the strain are in a relationship, right? They're related to each other. E equals stress over strain.
Is that, does that point have a side, is that just your yield?
Actually,
That failure
the
point.
true yield is right here. But this is called, yeah, this is what chapter 10 will do for us. This is called the proportional limit because it's the end of the straight line. And a straight line is proportional. Things are proportional to each other, right? You put in 1 pound, you get that much deformation right here. Put in another pound, you get that much. You put in another pound, you get that much, right? This is not a curve. It's not a parabolic curve or anything. It's not exponential. It's just a straight line, right? So all of these things are equal, and this is where E lives in this region. E does not live out here. It doesn't exist anymore. Modulus elasticity. The materials change. When you stretch them too much, they get harder, they get softer, they get brittle, they change. The molecular structure changes when you permanently deform something.
And is it different for temperature? Is there a different graph for every temperature?
Temperature is just a whole different dynamic that we're going to add to the problem. So when we do thermal stresses, we will calculate load stresses first, and then we'll add in thermal stresses and add them to the load stresses and go, oh, this is not good, or this is fine. Yeah. So it's kind of its own creature. All right. So that's good. And then this is the plastic region. Here, I should write it down below. This is a little bit of chapter 10. Plastic meaning if you take plastic and you pull on it, it stretches like Play-Doh, right? And then you let go and it stays stretched. So plastics don't have much elongation to them at all. They just permanently deform. They do it really well. Like you can take a piece of plastic and like stretch it way out and then let go of it and it just stays stretched way out, right? So that's why they call it a plastic region. And mild steel does this really cool thing of that. It gets harder. In the plastic region, it gets harder. As it's permanently deforming, it gets harder and stronger. So that's why we love it so much, because there's very few materials that do it as well. All right. So we can start to like, oh, all of these things are like interconnected. Like they're all, right? E stress, strain shows up here, stress shows up here. So I could write stress as P over A and put it on top, and strain as delta over L. Right? I just subbed in P over A for stress and delta L for strain, delta over L. I just subbed them in. Again, because they're all kind of related, we can make a nice big formula that has pieces. That's actually very common. So let's fix it because it's really weird looking, right? L moves to the top, A's down below, delta's down below. So a little bit of algebra goes PL over A delta. That was just algebra. The good news is we're getting to a formula you use all the time. So we're kind of just deriving it, which I don't normally do, but I think it's important that you know where this comes from. It comes from this, right? E equals stress over strain. That's where this came from. That's where this came from. And now I'm gonna solve it for the thing that we really like to know, delta, which means these two just switch places. Delta equals PL over AE. I've used it so much in my life, I just like PL over AE is just like the speed limit in life, you know, use it a lot. And it's how you get delta. So that's the same, this is the same formula as what we did here. We just did it in pieces. We just did it in all the pieces, right? But there's a common formula for it, and it's this. And this is calculated. Which means I'm not putting in any kind of a limit stress. I'm calculating the stress and putting it in. The stress is in there because P over A is in there, right? And the strain's in there, this L and E thing, it's all in the package. The thing is, you got to know 4 things to get it, right? You got to know load, length, area, and what material it is. This is the material property. This is the shape property, what shape it is. Is it a pipe? Is it a W shape? Is it a rectangle? Whatever. Length and load.
If it was a pipe, you would only do the area of the pipe.
That's exactly right. Just of the material. Yep. Most pipes you can look up, so you don't have to calculate that, but it would be just outer diameter minus inner diameter. You could get it. Yeah. So this is exactly what we just did here. We just did it in pieces. I just walked you through it in pieces. But they introduced this formula in this chapter because we want to know how much something changed. We need delta. Okay. All right, let's do one. And then I probably should do shear stress because you have some homework in shear stress. Oh, let's just make it up. Let's have our truss. We have our truss here. And it's got some upper chords and lower chords, right? And we determined this thing to be in 3 kips tension. And it's a 2x4. And it's 3 kips in tension. And it is 10 feet long. And it is made out of Doug fir. So how big is a 2x4?
1.5 by 8.4.
3.5 inches by 1.5 inches. And we want to know, so the question would be, how much does it deform? Tension means it's going to do what? And get bigger or smaller? Bigger. It's pulling apart. Tension means it's being pulled apart. Do we just go straight for deformation? Because that's the question, like how much does it deform? Is there anything we should check first?
P over A?
P over A first. We should check the stress first to even see if the deformation is predictable. Because it might not be, it might be just like, no, this is broke, right? Then it's not predictable. So yeah, we should do stress first. And that equals P over A. What's our load?
3 kids.
3K. What's our area?
5.25.
Perfect.
7.
What do we get for a stress? 0.571 KSI or 571 PSI. Right? What does Doug Fur think of that? That's why we do a stress, is to compare it, right? Well, let's look. Doug Fur, we want some kind of tensile stress, right? Anyone see it?
55.
Yeah, so tensile stress parallel to the grain is F sub T. Remember, we make our 2x4s out of the length of the tree, so the grain is going parallel to the load. So yeah, F sub T, Doug Fur, 625, and what's the unit?
PSI.
PSI, 625 PSI. And what did we calculate?
5.7.
571, we're right at it, but we're good. Right, we're under it. Perfect.
Wait, are we? Wasn't it?
I thought it was 6.
Oh, was it 6?
625. The limit is 625.
And you can go right up to.
You can go, I was just gonna emphasize that. Wood industry, you can go right to it. We don't even think about factors of safety because the wood industry does it for us. Like, we could have 624.5. I'd be like, hell yeah.
It
that
can't be
would-
added though.
It actually can be added. You can be right at it. The wood industry has put such large factors of safety on this thing.
Still like a tolerance on it? Like, can you go a tiny bit over that?
No.
Or is it just like?
Not, definitely not on the piece of paper that you're submitting, no. Yeah. All right, so it's good, right? So that means we can do our new formula, PL over AE. Yep. Our length is 10 feet. Our area. That's in inches squared. And we need an E value. For Doug Fur. Right? So it's PL over AE. And E is the material property. And Doug Fur gives us what? 1700 for E. KSI. Or 1,700,000 PSI. But KSI is fine. For our E value. 1700 KSI.
Should you convert the 10 feet to inches to keep it all in inches? So
Yeah, we got to. That's why I was putting all the units down, because what do we want for our unit in our deformation? Yeah, inch, not inch per inch.
oh, that's
Deformation is just inch. Right? We just want an inch. So we have to get rid of the kips. That goes away. So that worked. But now we have feet and inches, like we have a mess. So
120.
we've got to, yeah, we've got to get rid of those. These down below cross out. And we got to get rid of this foot into inches. So we know that there's 12 inches per foot. And now we have inches. Anybody else get that? Yep. Forty thousandths of an inch in the change for that 2x4. With 3,000
And
pounds,
that's a,
it gets longer,
stretch, right?
yeah, it gets longer. And that's the total, so the nice thing about this is it doesn't give you strain, doesn't give you like inches per inch or some kind of abstract concept. It gives you the straight deformation, like the, hey, it grew this much, 0.04. Okay. So that's what's nice about that. And then just the basic general rule of deformation is 1/360th of the length is kind of a rule for deformation. Meaning that of the 10 feet, so you take your 10 feet, get it to inches, and then divide by 360, and that's acceptable deformation. Super basic rule.
Is that 1 inch?
That's 0.3.
Oh, 0.3.
Yeah, 0.3.
That's a point.
So I took the 10 feet, got it to inches, that's 120. And then it's 1/360th. That's the basic general rule of thumb if you don't have any deflection to like compare to, which most of the time we don't. Then you just divide by 360 and you got 1/3 of an inch. We're way under that, right? Way under that. All right. Few minutes left. Let's do, is that good? We'll go through that a lot because it takes repetition. It really does. So let's talk about shear stress.
So I just need to make a key.
Oh, you will need to make, yeah, you'll need to sort this all out. All right, I just needed to make sure how they were going to identify shear stress. They use tau. Tau. I make a really good tau. You'll like it. That's my tau. It's another Greek letter. And it's for shear stress. All right, so let's just go backwards a little bit. What was compressive stress equal to? P over A. Yep. What was tensile stress equal to? P over A. What will shear stress be equal to? P over A. Yeah. Yep. P over A. So it's a different A is the important thing. So when we build, like wood is kind of one of the easier things to think about. Maybe this is a wall and this is the bottom plate. And maybe it sits on a beam. Right? And sometimes there's like a wall or studs that come off. Right? And the roof is coming down here. Everyone kind of see that? This is like some kind of beam. You know, it's being carried here and here. And the loads get spread out. Right? So what can happen is if this load is too great, it comes down, it's going to want to bend this thing, but more than likely it's going to want to just continue straight down and shear it off. Right? So there's metal shears, maybe you've been exposed to those where you put a piece of metal in, push a button and it goes, whoa, and it just shears off the metal. Right? That's shear stress. So if this load is coming down and the failure is here, I'm going to darken that cross section of this flat 2x4 or whatever it is, 2x6, this area fails because this shears off. That's different than what we had in tensile stress. Tensile stress, we had something and we were pulling on an area perpendicular to the load. So tensile stress and compressive stress, the area is perpendicular to the load. That's what we've been doing, right? Now, the load's coming down and the area is parallel to the load. Right? So they show you some diagrams of shear stress. I think this is a punch where a round punch is punching through a metal plate, right? And it pops one of these out, right? It just punches right through it. Well, it sheared off this area all the way around. That is a shear failure. If we want to calculate how much force is required to shear that off, then we have to calculate that failure stress, right? Here's another one where we have two things that are put together somehow, maybe with epoxy, maybe with glue, somehow put together, and we're going to pull on it here and pull on it here. And the area that's holding it, everyone see that area? It's this rectangle right here. That's your shear stress area. That area is parallel to the loads. That makes sense? I'm emphasizing this because this is how you tell. Like, I'm going to give you things and say, well, calculate the stresses. What do you mean? Well, this piece right here is being pulled on by that. Agreed? What kind of stress is that? That's a tensile stress. We've been doing that. So I could say, well, what's the tensile stress of part 1? Right? And this load pulls on this piece. I could say, what's the tensile stress of part 2? And then I could say, what's the shear stress of this system? Well, that's this area. So all of those are 3 different areas and potentially 3 different stresses if this was a different material than this or a different size than this. Okay? So the shear stress is this area is parallel to it. All right. Here's another example of it. Shear stress. So it's the same formula. You got to calculate P over area. So we don't need to practice a formula. You've been doing that. We just need to practice like, oh, in our head, what is it? So here's a system that's bolted together. And again, we're going to pull on this and we're going to pull on this. And if it fails, how would it fail? Like this. So when you're calculating shear stress, you have to calculate the area that would fail. So that could be 2 bolts and 2 areas. That could be, if there's 8 bolts in the connection, then there's 8 areas that have to fail. So think about what's got to fail, and that's the area I got to use.
Is that how that famous example happened?
There's a few of them. Yeah. Well, it gets trickier when you go for kind of ear type connections to see if they have one. Yeah, like a clevis connection. Oh, this is a good one here. Oh, lost it. I'm not in equilibrium. Right, so we got a load here and a load here. And we got a rod and a clevis. Okay. I need to calculate the shear stress. Clearly, we got some shear going on here, right? How many areas have to fail? So this could get removed, right? And then this could be up here. So then these 2 areas got to be removed. They got to fail for this thing to go. So this is a 2 area failure, not a 1, 2, 3, 4 area. Now, all 4 don't have to go, right? So you just have to think about like, oh, I got to calculate the area. And is it the area of the rod or is it the area of the hole? Because the rod and the hole probably are not the same 2.
The rod.
Yeah, it's definitely the rod's got to fail, right? So we have to think about like, oh, what's got to fail? How many of them are there? Right? So that's it. That's it with shear stress. Other than the kind of glued surfaces. So what about this one? We're going to push down on this and we're glued here and here. What's got to fail?
The glued areas.
Those 2 glued areas both have to go. Right? Not just one. Both. Because these 2 are working together for this to drop, this glued area and this glued area. We do a lot of construction glue, right? We glue plywood to floor joists, we glue plywood to trusses. Those are all designed connections.
In a glue joint, is it the glue breaking? or is it the
Absolutely.
glue
That's exactly what
touching
I was leading you to. Like, when you calculate that shear stress of a glued joint, you compare it to the properties of the glue that was used. So when we're laying up a roof and laying that plywood on the roof and gluing it down, you can't just go by Gorilla Glue. What's the properties of that? Who knows, right? You have to use liquid nails rated at whatever. So that's what you would compare it to. If you're using epoxy, then there's always ratings on epoxy. So that's what you compare it to.
And would that be true for like, if it was pin connection or something where it was the different kind of material?
Absolutely. Bolted connections, is it a grade 8, a grade 5, a grade 4, a grade 3? Is it stainless steel? Is it hardened? On and on and on. Yeah. But the formula is P over A. We don't have to practice that. Let's practice getting the right area in. All right, you have some homework to do. Use the new symbol too for shear stress. And what is it? It is 17, 20, and 21. Pretty sure those are all. Shear stress is 17, yep, 20 and 21. All shear stresses. Maybe a little statics in there too, to keep you fresh. Books there if you need it. Good job.
Can I see how you would do, problem 6?